Okay, so we started 10 minutes late, so I'm not going to go over. We're going to have a 70-minute lecture today, which means I'm definitely not going to finish what I wanted to, but it's okay. So I'm going to, remember I said that chapters 1, 2, and 4 of Do Carmo are things that I'm kind of assuming are review, even though I know they're not review for everyone. And so I'm going over those quickly and letting you fill in the gaps if there are any gaps you want to fill in. But right now we're in chapter 3, which I'm going very, very carefully through. Chapter 3 is about geodesics and about a lot of technical properties about geodesics. We're gonna prove a bunch of technical results today and Wednesday, which are going to give us a feel for what geodesics are telling us. So we're going to prove eventually that a geodesic, as long as the 2 points are close enough together in some precise sense, a geodesic is the unique curve joining those 2 points, which has smallest length. It's called locally length minimizing. And any curve between 2 points, no matter how far away they are, if it is a minimizing curve, in other words, if its length is less than or equal to the length of any curve between those 2 points, then it must be a geodesic. But it's not always true that if 2 points are not close enough together that there will exist a minimizing curve between them, right? That's going to be related to the notion of completeness. And we're also going to prove that in a Riemannian manifold we can find locally every point lies in an open neighborhood that has very nice properties. So first there'll be a normal neighborhood, then there's going to be what's called a totally normal neighborhood, then there's going to be a geodesically convex neighborhood. These are going to be more and more technical, but they're going to be useful for us later in the course. So I'm going to be going very slowly today and Wednesday to go through the whole chapter 3. And then we're going to very quickly review curvature the following week, and then again slow down when we get to chapter 5 and higher. Okay, so we're going to start talking about minimizing properties of geodesics. We're probably not going to get to the state. Well, we'll get to the statement. I don't know if we'll get to the proof. We won't get to the proof today. It'll be on Wednesday. But before we can make this precise, we need to enlarge the class of curves that we're going to allow. We're not only going to allow smooth curves on a manifold. We're going to allow it to basically, they're going to still be continuous, and they're going to be what's called piecewise smooth. So they'll be allowed to take a finite number of sharp turns, but they're still be continuous. So here's the definition. A piecewise smooth curve alpha, this piecewise smooth curve on M is a continuous map alpha from some closed bounded interval into M with a partition A is T naught and then less than T1, T2, up to T, let's say N, which is B, such that the restriction of alpha to Ti minus 1 comma Ti, which is a map from Ti minus 1 Ti to M, is smooth. Okay, and remember, what does it mean for a map on a closed bounded interval to be smooth? It means that there's some extension to an open interval containing this, which is smooth and whose restriction is this. Okay, so in other words, I draw a picture, we're allowed to take, as I said, a finite number of sharp turns. So this might be alpha of T naught, T1, T2, T3, T4, for example. And let's define, so we allow a finite number of jump discontinuities in the velocity. In the velocity vector field of alpha. Okay, so we can now be a little bit more precise. Let's let alpha prime minus at Ti be the limit as T goes to Ti from below of alpha prime of T, and alpha prime plus at Ti is the limit as t goes to ti from above of alpha prime t. And the vertex angle at alpha of ti is the angle from alpha prime minus ti to alpha prime plus ti in the tangent space to M at alpha of ti. So in the picture, let's go back to the picture. So you see there's a limiting velocity here as we come from below. This is alpha prime minus of t1, and this is alpha prime plus of t1, and there's this vertex angle here. Okay, that's not going to really play a role today, except in a minor way, but it's gonna show up often later. Okay, and let me just make a remark. We can define parallel transport along piecewise smooth curves. Why do I feel like I said this already? Maybe I did. Piecewise smooth curves by basically parallel transporting along each smooth path and composing alpha n, where alpha I is alpha restricted to ti minus 1 ti, I equals 1 up to n. Okay, so we have a vector. We have some vector here, vp, where alpha t naught is alpha 0, alpha a is alpha t naught is p. We know how to parallel transport it along this smooth curve, and then we parallel transport it along this smooth curve, and then this one, until we get to the end. Okay, so we're going to be doing that, and the properties of parallel transport, parallel transport we saw is not just an isomorphism but an isometry, right? So even if we're composing a finite number of isometries, it's going to be an isometry. This is an isometry from t alpha a of m to t alpha b of m. Okay, and let me make one more definition. Let gamma be a piecewise smooth curve. On M, we say gamma is minimizing if the length of gamma is less than or equal to the length of alpha for any piecewise smooth curve alpha with the same endpoints. Alpha, let's say, with the same initial and final points. Or here, this is a better way to say it. Any smooth curve alpha from gamma of A to gamma of B. Okay, so here's gamma of A, gamma of B. If I had a curve that had the property that if I took any other piecewise smooth curve with the same initial point and the same final point, the length is no smaller than the length of gamma, then gamma is a minimizing curve. Now, there may not exist, given 2 points, there may not exist a minimizing curve between them. I'll write that over there. If the manifold is connected, we know there exists a continuous curve between them, because connectedness for manifolds is the same as path connectedness. And then by modifying it a little bit in each chart, it's easy to see we can get a smooth curve between them, but it doesn't mean there's going to be a minimizing curve. So note, if M is connected, then any 2 points P and Q and M can be joined by a smooth curve. Doesn't even have to be piecewise smooth. You can smooth it out at the edges, but there may not exist a minimizing curve. And it's easy to see an example of that. Let's take Rn and take out a point. I might as well take out the origin. If I take Rn minus the origin with the Euclidean metric, we already know from high school geometry that the shortest path between 2 points is a straight line. So if I take 2 points so that the straight line from them would have to pass through the origin, that curve doesn't exist on this manifold, right? And you can see there is no minimizing curve between these 2 points, because no matter what curve I take, I can find another curve in this manifold, which is closer to this one that doesn't exist, that has a smaller length. Okay, so this is obviously some kind of cheap example where I took a nice manifold and I removed a point, right? But we'll see that there's a reason why I had to pick an example like this, that the fact that this failure of there to exist a minimizing curve between 2 points is exactly what's called being not complete. Okay, so that's an aside. It'll come in a few more weeks, or at least a week or so. But I just want you to remember there may not exist a minimizing curve between 2 points. One of the things we'll prove by the end of Wednesday is that if the 2 points are close enough in some precise sense, there will exist a minimizing curve and it'll be unique. But if they're too far apart, that might not happen. Okay. So the goal for the next couple of lectures, for today and Wednesday, the short-term goal, will show that a minimizing curve, if it exists, right? It may not exist. Minimizing curve must be a geodesic. In particular, it must be smooth, right? Because I define a minimizing curve as a piecewise smooth curve with a certain property, but all geodesics are smooth. And it's not an if and only if. We'll show any geodesic is locally minimizing. So I haven't told you what this means, which is why I'm putting in quotation marks, but we're going to see exactly what it means. Okay, but before we can get there, we need some technical lemmas. Well, one technical lemma, which is called the symmetry lemma, which is very easy to prove. We're going to be using it all term. And another very, very important thing, which should be a theorem, but it's called the Gauss lemma, because there's like 1,000 things named after Gauss in Riemannian geometry. This is the first one you're going to see. There's a Gauss lemma, a Gauss equation, a Gauss map. This one is called the Gauss lemma, but it's important enough that it really should be a theorem. Before we get there, we need some definitions. This is the definition of a parametrized surface. Okay, so let's let A in R2 be a connected set with U contained in A contained in U bar for some open set U. I mean, basically what you should think of is that it's a connected set and it contains its interior and it may not contain its entire boundary. So you can take U to be the interior of A. It's a connected set. So A is a connected set containing its interior. Obviously, it contains its interior. And possibly some, but not all, or possibly not all of its boundary points. So these are contain subset or equal to. Right? So the only real examples we're going to need are going to be things like this. So examples. This is in R2. Right? So this is a picture of R2. Let's call it the S and T axes. Here's some examples of these A's. I can take something that's bounded by some closed curves like this, where I have this part of the boundary, but I don't have this part. Here's an example. Here's another one. And it's going to be usually things like this. And then I just realized I forgot to finish the definition. Let A be such a connected set such that the boundary of A is the image of a piecewise smooth curve in R2 with vertex angles not equal to pi. Okay, so so that really means, what would it mean for the vertex angle to be pi? It means you're taking a 180-degree turn at that point. We're going to avoid that, and you see in these pictures, none of those have that, and you'll see why in a second. Okay, so that's the type of set we want. A parametrized surface in M is a smooth map sigma from such a set A into M. Okay, and what does it mean to have a smooth map on a set like this? It means it's the restriction to A of some smooth map that's defined on an open set containing A. So restriction to A of a smooth map defined on an open set containing A. Okay, so let me just make a note. The reason we want the vertex angles to be not equal to pi, we want the vertex angles not equal to pi to ensure that the push forward at some S naught T naught, which goes from the tangent space S naught T naught of R2, which is canonically R2. This is, yeah, that's true. To T of sigma S naught T naught M, that this is well defined. In other words, we want the partial derivatives, even at the boundary points, to make sense. All the partial derivatives, all the directional derivatives, to make sense even at the boundary points. And you can see that if you took a 180-degree turn, then there's some ambiguity about how to define the sigma star at that point. Don't worry about this if it's not immediately obvious to you, because we're never going to have a problem with it. Yeah.
About the definition.
Yep.
So I'm just curious about the condition.
Yeah, I mean, this is you. Yes. Yeah, I guess this is some non-empty, right? Let's just say it better this way, right? Connected set with non-empty interior. I like that better. Okay. I mean, basically, you should always be thinking about this. Yep. No, it doesn't have to be something connected. You can have an annulus. Yeah. It is. I didn't say the piecewise smooth curves had to be connected. I guess you're right. No, you're right. You're right. You're right. So then it has to be simply connected, right? It looks like this or this. Let's not spend too much time worrying about exactly what it is. Really, what I want is I want this sigma. I mean, I'll say it right now. I want to think of these sigmas as being one parameter families of smooth curves. Okay, so let me say that now, and maybe you'll be happier. Yeah. No, I'm not saying that. I'm saying I don't want to think about this. That's what I'm saying. Okay. Think about this. Okay. Okay. So notice if sigma naught T naught is in A, then I can look at the map T goes to sigma of sigma naught T, or I can look at the map S goes to S sigma of S T naught. These are both smooth curves in M. Really, what I want is when I fix, a point in A, I want there to be at least a half interval where this makes sense as a curve, right? So I can think of sigma, this parameterized surface, as a one parameter family of smooth curves. So sigma of ST, you can think of fixing S and being a function of T, or you can think of fixing T and being a function of S. These are two one parameter families of smooth curves. On M. Okay, so I can think of T as being the parameter for each of these curves, and sigma and S is telling me which curve to take, or vice versa. Okay, let me draw a picture. So here's A, and this is the boundary, the piecewise smooth curve. So I can look at manifold M, and I can look at, remember, this is the ST plane. So these yellow vertical lines are the ones where S is a constant, and I think of them as functions of T, and this is going to give me curves on the manifold, and I can also fix T and vary S. That's going to give me horizontal lines here, and these are going to give me curves on the manifold. But the picture is misleading because sigma doesn't have to be an immersion. Sigma need not be an immersion. It's just a smooth map. Okay. So these are the way we're going to formalize smoothly varying one parameter families of smooth curves. And now, as we did when we talked about curves last week, and we talked about vector fields over a curve, we're going to talk about vector fields over a parameterized surface. So a smooth vector field along a parameterized surface, sigma, is a smooth map V from this domain A into the tangent bundle such that V of S naught T naught is in the tangent space to M at that point for all S naught T naught in A. Okay, so it's exactly what you want it to be. And again, if you know about pullbacks, it's just modulo the fact that this A might not be a manifold because it has a boundary. It's just a section of the pullback of the tangent bundle of M by this map sigma. And so note, T goes to sigma, goes to V of sigma of S naught T, and S goes to V of sigma of S T naught are both smooth vector fields along the curves. T goes to sigma of S naught T and S goes to sigma of S T naught respectively. Okay, so if I fix one of the two parameters in my parameterized surface, I get a smooth curve. And if I take a vector field, smooth vector field along that parameterized surface and fix one of the two parameters, I get a vector field along those curves. Okay, so in particular, when we have a vector field along a curve, we know we can take its covariant derivative along that curve. So if I write dsv at S naught T naught, this is the covariant derivative of V along the curve. S goes to sigma of S T naught at S equals S naught, and dTV sigma naught T naught is the covariant derivative of V along the curve. T goes to sigma of S naught T at T equals T naught. So this goes back to the discussion I said when this notation was ambiguous, right? This D, but because I'm fixing these two different parameters, when I write a ds, I mean I'm fixing T naught and thinking of it as a curve in the S parameter, so I can covariantly differentiate. And if I write dt, that means I'm fixing S and thinking of it as a curve in the T parameter. Okay, so now we're ready for this first technical result, which is called the symmetry lemma. Symmetry lemma. So let sigma be a parameterized surface. Actually, okay, that's fine. Then d sigma ds and d sigma dt are smooth vector fields along sigma. So maybe I forgot to make that precise. Yeah, I drew a picture and I forgot to write this. So before I state the lemma, so why are these smooth vector fields along sigma? What is d sigma ds at S naught T naught? Well, that's d by dt at S equals, sorry, d by ds at S equals S naught of sigma T naught, right? So if I fix T naught, it's a curve in S. And I want to look at the velocity of that curve at S equals S naught. But by the chain rule, this will be the push forward of sigma at S naught T naught applied to the vector d by ds at S naught T naught in R2, tangent vector, and this is in T sigma of S naught T naught of M. Okay, and similarly, d sigma dt S naught T naught is d by dt at T equals T naught of sigma S naught, and that's sigma star S naught T naught of d by dt at S naught T naught in the same tangent space. So all I'm saying is if we fix one of the parameters and think of it as a curve in the other parameter, then we can take its velocity vector, right? And that's a vector field along the curve, but we can vary that other parameter that was fixed, and we really get vector fields along the surface. Okay, so the symmetry lemma says that I can take the velocity vector field, I can take this vector field along sigma, and I can take its covariant derivative in the t direction, and it's the same as doing d sigma dt and differentiating it in the s direction. So these sigmas, if I look at this yellow curve and I look at the velocities of these yellow curves, that's going to give me a vector field along this surface. And if I take the covariant derivative of that vector field along the blue directions, blue curves, I'm going to get another vector field along this surface. And it's the same as doing it everything in the opposite order. Okay, so let's prove this. Question? Yep. Nothing else would have made sense, right? Okay, so we're going to prove this by proving that these, what are these? These are both vector fields along sigma. Okay, we're going to prove that that they're the same, they give you the same value at every S naught T naught. So let's let P be sigma of S naught T naught in M, where S naught T naught is in A. And let's let X1 up to Xn be local coordinates for M in a neighborhood of P. Okay, then I can write sigma of ST is going to be some X1 of ST up to Xn of ST. Again, I'm using the usual convention of abusive notation where I'm identifying the image with its coordinate representation. This is really the coordinate representation. Maybe let's put that up there. And then what is d sigma ds? I think of this, I think of t as being a fixed parameter and thinking of this as being a curve in S. So we know we have to differentiate the, I'll put partial derivatives because these are functions of S and t. We have to differentiate with respect to the parameter times d by dxi, right? That's what that one is, and d sigma dt is dxi dt, let's say dxj dt, d by dxj. So now let's calculate dt of d sigma ds. This is dt of dxi ds d by dxi. Now remember how we compute covariant differentiation along a curve. This is some function of the parameter t, and then these are the coordinate vector fields. So this is going to be, first I differentiate the function of t with respect to t, and then this comes through, and when I want to differentiate that, I'm going to get a dxj dt gamma j I k d by dxk. Okay, so this is from the formula of covariant differentiation along a curve. So now what happens if I interchange the roles of S and T? If I compute ds of d sigma dt, I'm going to get d squared xi ds dt d by dxi plus dxi dt dxj ds gamma k ji d by dxk. And let's look at these. These two are equal because these are smooth functions, so we have equality of mixed partials. And why are these equal? The difference here, these two terms would be the same as these two terms if I swapped I and j. But the Christoffel symbols are symmetric in I and j in local coordinates, and that's what these are. So I'm out of room, so I'll write it on the board on the left. So ds of d sigma dt equals dt of d sigma ds because of two facts. First of all, d squared xi ds dt is d squared xi dt ds because sigma is smooth. So of course it's at least C2. And it's not enough. Gamma kij equals gamma kji in local coordinates because the Levi-Civita connection is torsion free. I don't remember if I actually said this in the lecture, right? But I think I did. The fact that the second defining property of the Levi-Civita connection, one was that it was metric compatible, the other one was torsion free. If you write that property in local coordinates, it exactly says that the Christoffel symbols are symmetric in I and J. So if you know more general connections, if you try to establish the symmetry lemma more generally, this part would be fine because you're always working with smooth things. But that symmetry lemma would not be true if your connection wasn't torsion free. Okay. So I like to emphasize where we really use the properties of Levi-Civita connection. Here's one place where we definitely need the torsion freeness. And there will be lots of places where we use the metric compatibility today. Okay. So the next thing is the Gauss lemma, which, as I said, is so important that it should be a theorem. But before we get to it, so here's an aside. Let's let V be a tangent vector to M with V not equal to 0. Suppose we have a non-zero tangent vector. And suppose V is in the domain of the exponential map. Okay, what does this mean? This means that xp of V is defined. And what was xp of V? You take the geodesic with initial point P and initial velocity V, and you follow it for time 1. Okay? But because this vector is non-zero, I can write V as the norm of V times V over the norm of V, and I have a 1. And then by rescaling lemma, I can write this as gamma V over norm V times norm of V. So this is another way to think of what does it mean to take the exponential map on some vector V. You take the geodesic whose initial point is P and whose initial velocity is the unit vector in the V direction, and you follow that geodesic for a time equal to the norm of V. So if V is in the domain of x of P, xp of V is gamma V over V. We follow, i.e., we follow the unit speed geodesic with initial data, initial point P and initial velocity V over norm V for a time equal to the norm of V. Okay. So V being in the domain of xp, another way to think about what it means that if you take the geodesic, at least for V non-zero, because we know if V is 0, that xp of 0 is P, right? If V is non-zero, xp of V being defined means that if you take the geodesic with this initial velocity, V over norm V, that it is defined at least up to time norm V. So of course, it'll be defined for any time less than norm V. So hence, xp is also defined for t less than, let's say t less any t from 0 to norm V. Okay, because this gamma is defined up to here. The punchline of this is that the domain of xp is star-shaped with respect to the origin, to the 0 vector. This says that the domain of xp is star-shaped with respect to the origin, i.e., if V is in the domain of xp, so is TV for all t from 0 to 1. Okay, so the domain TPM, whenever you have a vector that's in the domain, then any positive multiple of it between 0 and 1 will also be in the domain. Something I should have probably said earlier. Now, armed with the symmetry lemma, which I have to erase, but is very easy to remember, we can state and prove the Gauss lemma. I can definitely do it. As I said, this is so important, even though it's called the Gauss lemma, I'm going to call it a theorem. The Gauss lemma. Okay, so let's state it carefully. So let P be an M. Let V be a tangent vector at M such that X P of V is defined. So in other words, V is in the domain of X of P. And let W be another tangent vector to M at P. But I'm going to think of this space as the tangent space at V of TPM. Remember, TPM is a vector space. So the tangent space to a vector space at any point in that vector space is canonically isomorphic to the vector space itself. So here's a picture. This is TPM. If I have some vector V, V is in TPM, then I'm going to think of the tangent space to TPM at V is just a copy of TPM attached at the point V. And this W is a vector in TPM, which I think of as emanating from V. Okay, so I haven't stated the lemma yet. Then I can look at X P star at V. This goes from TPM to T X PV of M, right? Because XP takes the point V to XP of V. Sorry. Yes, and this is TV of TPM. Okay, so let's, before I write, what's going on here? This XP is mapping us. Where does it send V? It sends it to XP of V. So the push forward will go from the tangent space to the domain at the initial point. So it's going to go from TV of TPM to the tangent space of the image point in the codomain, TXPV of M. Okay, so, but we can identify these, right, canonically. So the push forward of XP at V is a linear map from here to here. We don't know that it's an isomorphism in general. We know that when V equals 0, if V is 0, this is also a P, and not only is it an isomorphism, but it's the identity. So we know if V equals 0, then XP star of 0 is the identity on TPM. So of course it's an isomorphism, and because everything is smooth, if you're close to the identity in some precise sense, you'll still be invertible. So XP star V is invertible if V is sufficiently small. But we don't care about that here. We don't care here. Okay? Because it's not true that this thing will be invertible for all V in the domain of XP. For all V, right? Yeah, for all V in the domain of XP. That's not necessarily true. That's going to be very important later, because this is going to be related to what's called conjugate points and cut points for geodesics. Okay, but for now, all I'm saying is that V is in the domain of XP, and therefore the push forward of xp at v is some linear map from TPM to txp of v of m. It's linear, it may not be invertible, doesn't matter. What does the Gauss lemma say? It says the following. So then I can look at xp star at v, and I can apply this to v, and I can also apply this to w. This inner product is equal to VW, inner product. So let's make sure we understand what's happening. First of all, this inner product, this is the inner product. Sorry, my phone keeps ringing. I just want to make sure there's no disaster. Okay, no. My daughter walked to school by herself today, and she was supposed to text us when she got there, and she never did, but we expected her to forget. Inner product on TPM, because V and W are both in TPM. This is the inner product on TXPV of M, because both of these things are in XPV. The other thing I really want to emphasize is this is the same V. We're not saying that XP star is an isometry. We're saying that if one of the vectors is V, and doesn't matter what the other one is, then it'll preserve the inner product. Okay? So it's not in general an isometry. Okay, so let's prove the Gauss lemma. Okay, so proof of Gauss lemma. So in the book, Docarmo does it kind of quickly. I'm going to put in all the missing details. And so he handles some cases with one sentence, and there's a whole bunch of stuff he's sweeping under the rug. So it's true if V equals 0, because XP star at 0 is the identity. Right? We already mentioned that down there. So if V is the 0 vector, of course, the identity map is an isometry for any V and W. Okay, so let's assume V is not 0. And let's look at the first case, case 1, when W is a multiple of V. Okay, this is supposed to be true for any W. We're going to first prove it when W is a multiple of V. And because both sides are linear in W, if we can also show it for vectors W that are orthogonal to V, then it'll follow for all W. Okay, so let's look at what is XP star at V applied to W. Well, how do we calculate the push forward at a point? We just take d by dt at t equal to 0 of xp applied to some smooth curve alpha t, where alpha of 0 is V and alpha prime of 0 is W, which is lambda V. Right? This is a curve. This is a curve in TPM. Okay, well, let's choose alpha of t to be V plus t lambda V. This definitely passes through the point V at time 0, and its velocity at time 0 is lambda V. This is equal to 1 plus t lambda V. So this becomes d by dt at t equal to 0 of xp of 1 plus t lambda V, which is d by dt at t equal to 0 of gamma. The definition of xp, we take this vector and follow it for time 1. And then by the rescaling lemma, this is gamma of gamma v of 1 plus t lambda. And then by the chain rule, that's equal to lambda times gamma prime v of 1 plus t lambda evaluated at t equal to 0. And that's lambda gamma v prime at 1. When t equals 0, I get 1 there. Okay, so this guy is lambda times gamma prime of 1. So let's calculate both sides of the Gauss lemma. We just showed that, well, this one is just, this is the same thing when v equals, remember, w equals lambda v, right? So this calculation I did, if I just replace lambda by 1, I get what I want. So this is gamma prime of 1 times lambda gamma prime of 1, which is lambda gamma prime of 1, sorry, gamma v. But geodesics have constant speed. Constant speed. So this is the norm of the velocity at time 1. So this is the same as gamma v prime of 0. Gamma v prime of 0. And that's just, well, what's this? That's just v. And I can bring the lambda in, and that's vw. Okay. So I think Docarmo says, by the definition of the exponential map, it's true when w is a multiple of v. But there's something to write down there. It's not immediately obvious. So we've proved it when w is a multiple of v. As I said, now both sides are linear in w. So it's enough now to prove it if w is orthogonal to v. So since both sides of the Gauss lemma are linear in w, it's enough now to prove it if w v is 0. Okay, so the Gauss lemma that we're trying to prove, now we're going to assume w is orthogonal to v. We want to show that this is also 0. Okay. So the first thing to observe is that since xp is defined at v, and the domain of xp is open, is one of the things I glossed over when we were talking about the exponential map, but it's easy to check. There exists some epsilon positive such that xp of u is defined for u equals t times v of s, where 0 t is less than 1, minus epsilon s less than epsilon, where v from minus epsilon to TPM is a smooth curve with v of s norm is 1 for all s. And this is because xp is star-shaped with respect to the origin. And because the domain is open, right? So I know that I can move a little bit. Here's a picture, right? So this is v. I know the exponential map is defined there. If I draw the unit sphere through here, then I know if I had a curve, a small curve on this sphere, this is v of s, where, so we want v of 0 equals v, sorry. If I have a smooth curve on this unit sphere passing through v at s equals 0, then the exponential map will be defined at all those points, and also this whole cone, right? I can multiply by t when t goes from 0 to 1 because of the star shapedness. Okay, I have to fix a typo in my notes. Well, it equals V at time 0. Yeah, that's why I called it V. Okay, so this is V, and V of S is a curve on the unit sphere in TPM with the inner product GP. Okay. So sorry, yeah. So we can choose V of S such that V of 0 is V and V prime of 0 is W, because W is orthogonal to V. So here we're using the fact that the for the unit sphere in Euclidean space with the standard inner product, if you want, the tangent vectors to the sphere are exactly well, what's a tangent vector to the sphere? It's going to be the velocity at that point of a smooth curve that lies on the sphere. But because V of S is 1 for all S, when you differentiate this, you get V of S, V prime is 0 with a 2 if you want. And then you evaluate it at S equals 0. Let's do it like this. Okay, so the tangent vectors to curves on the sphere, if you think of the sphere as being in Rn, it's exactly those vectors which are orthogonal to the position vector here, V. So because now we're in the case where W is orthogonal to V, we can find a curve on the unit sphere passing through V at time S equals 0, and whose initial velocity V prime of 0 is this vector W. Okay. So now we are going to construct a parametrized surface and use the symmetry lemma. Okay. So consider the parametrized surface sigma from A to M, where A is the set of all S and T such that S is between minus epsilon and epsilon, and T is from 0 to 1. So this is definitely of the class that we're considering, given by sigma of ST is going to be XP of TV of S. And we constructed this set so that this is in the domain of XP for all ST in A. And we can apply XP to that. Okay, so let's draw a picture. This is TPM. There's V. The curve sigma of S is on the unit sphere. You can't really, it's supposed to be. See the picture, now I'm drawing TPM to look two-dimensional, right? So this has to be part of a circle. And then W is orthogonal to V. It's the velocity of, sorry, this is V of S. V of S. And XP is taking us to our manifold. Here's XP of V. I can look at, if you want, all the radial lines coming out of the origin. Those correspond to geodesics. These green lines are emanating from the origin. The exponential map sends them to geodesics. And this red curve becomes some red curve here. This is XP of V of S. Okay, so the curves T goes to sigma of S naught T are geodesics emanating from P, because if I fix S naught, this is just xp of T sigma of S naught. Okay. And in fact, sigma of S naught has length 1 for any S naught between minus epsilon and epsilon, for all S naught in minus epsilon epsilon. So in particular, so this is a unit speed geodesic. Okay, because the velocity of this at time 0 is sigma of S naught, which is a unit vector. Okay, so this parameterized surface, when I fix sigma naught and I vary T, I get unit speed geodesics. And let's compute the sigma ds at 0, 1. So this is s equals 0 and t equals 1. Well, how do we do this? By the chain rule. Well, first of all, sigma of 0, 1 is xp of v. Because if I take s to be 0, v of 0 is v, right? And t is 1, I get xp of v. So this is going to be sigma of 0, 1, which is v, which is xp of v. Sorry. This is not going to be, this is going to be tvs at 0, 1, and that's just v. Okay, the domain, and this applied to d by ds at 0, 1 of tvs. Okay, so I have to take d by ds of this at s equals 0 and t equals 1. I can put t equals 1 right away if you want, and then v prime of 0 is w. So this is xp star v of w. Okay, and what about d sigma dt at 0, 1? Again, that's going to be xp star v applied to d by dt at 0, 1 of tvs. Again, sorry, 0, 1. You can put v equals 0 right away if you want. And this is going to give me v. This is going to be xp star v of v. So what we've shown, so hence, the left-hand side of the Gauss lemma in this case, is, remember, it was the inner product of that with that. So it's just equal to the sigma dt at 0, 1, inner product the sigma ds at 0, 1. So we need to show this is 0. We need to show this is 0 because the right-hand side of the Gauss lemma in this case is 0. And I think I have just enough time to do it. I haven't used the symmetry lemma yet. So how are we going to show that that's 0? Well, one way to do it is to show that it's constant and that it's 0 at some particular time. So that's what we're going to do. So if I take d by dt of d sigma dt, d sigma ds, then by metric compatibility, remember, when we talked about covariant differentiation along a curve, we saw that if we had an inner product of two vector fields defined along the curve and we took d by dt, then that's equal to dt of this inner product that plus this inner product dt of this. So that's going to be dt of d sigma dt, d sigma ds plus d sigma dt dt of d sigma ds. Okay, but this one is 0 because sigma t goes to sigma of s naught t are geodesics. When you fix s and you just vary t, you get geodesics. So this is the velocity field of that geodesic, and we take the covariant differentiation in the direction of t. That's the acceleration. So this part is gone. And now this, by the symmetry lemma, this is equal to d sigma dt ds of d sigma dt. I can swap these s and t's. But then again, by metric compatibility, because now these are both d sigma dt's. This is 1/2 ds of d sigma dt, d sigma dt. Sorry, d by ds. But now we go back here and we recall that for any sigma, not only are we getting geodesics for as we vary t, they all have the same speed. They're all unit speed. But we know that this is a constant in t, but it didn't necessarily mean it would be independent of s. But it is because they're all unit speed. So this equals 1 for all s in minus epsilon epsilon because they're all unit speed geodesics. So I have a constant function 1, d by ds of that is 0. So this function here, the inner product of d sigma dt with d sigma ds, is independent of t. I've got one more line. So d sigma dt, d sigma ds is independent of t. And that means that if I want to calculate this at 0, 1, it's the same as calculating it at 0, 0. Okay, but what is, sorry, this is an s. What is d sigma ds at 0, 0? Well, that's going to be xp star 0, because this thing has to be tvs at 0, 0, and that's going to be 0, of d by ds at 0, 0 of tvs. Okay, and again, because I'm taking d by ds, I can put t equals 0 already. So this one is 0. So it's true this is the identity map, but it doesn't matter because it's a linear map. It's going to take 0 to 0. Okay, so this vector here, this is d sigma dt at 0, 0, d sigma ds at 0, 0. I don't care what that is. This is 0, and this is bilinear, so we get 0. Okay, so that's the proof of the Gauss lemma. I have 1 minute, so I'm just going to say what it means geometrically. Okay, and then we're going to use it on Wednesday to prove that the geodesics are locally length minimizing. Okay, this lemma is a good exercise in making sure you understand all these objects. So what does it mean? So let's look at TPM, and let's suppose the domain of XP is, well, we know it's some open set containing the origin, and it's star-shaped with respect to the origin. So I can find some closed ball. I'm using the inner product GP. Okay, this is the set of vectors in TPM such that V is epsilon, and this is contained in the domain of xp. Okay, I know that for small enough epsilon, I will be able to find a closed ball like this containing the domain of xp. And what it tells me is that the exponential map is going to map me to a manifold the origin is going to come to here. This orange set doesn't have to look anything like a ball, and the image of the yellow set is going to be something bigger here. What it tells me is that if I have a vector which is tangent to this sphere, then that's going to be orthogonal to the geodesics passing through that point. So this, I need one more color. If I look at this line here, there's a geodesic coming through here. So the radial line gets mapped to a geodesic, and this tangent vector is tangent to this sphere, constant radius sphere. All it tells me is that this angle is 90 degrees. That's what the Gauss lemma tells us. Okay, it doesn't tell you anything about the exponential map, the push forward of the exponential map being an isometry away from the origin. At the origin is the identity, so it's an isometry. Away from the origin, it doesn't have to be an isometry, but it will preserve the angle between these radial geodesics and these tangent vectors to the spheres of constant radius. Okay, that's what the Gauss map says. So on Wednesday, I'll repeat the statement. Maybe I'll draw this picture again, and then we're going to prove that if you have a geodesic, then it's locally length minimizing. And we're going to prove that if you have a minimizing curve, it must be a geodesic. And then I think we're going to start to prove that any point has reasonably nice neighborhoods. So there's a totally normal neighborhood, then there's a geodesically convex neighborhood. So we probably need Wednesday and like a third of next Monday to finish chapter 3. And then, as I said, we're going to go quickly through chapter 4 because I want to assume that it's a review. And then we're going to slow down again when we get to chapter 5, and we'll see how far we can get. Yeah.
So I don't know if this is just my ignorance, but this Gauss lemma seems so like intense, but yet it seems so lackluster.
Yeah, that's right. It's a very simple geometric fact. It's very easy to understand what it says. It's not so easy to prove it, right? And I should say, I'm going to give you it's such an important theorem. I'm going to give you another proof of the Gauss lemma when we're in chapter 5 talking about Jacobi fields, and it's going to be independent of this, right? It's not circular logic, right? But it's always good to know multiple ways of proving something that are, independent. But you're right. I mean, it's a very simple statement, a very deep. It's a very complicated proof. Yeah. Okay, so that's it.